Dear children, I am Swaranjit Kaur and today I am going to teach you about pressure in fluids and atmospheric pressure. Please watch this video till the end for the clear understanding of this chapter. I will start with thrust. What is thrust? Thrust is the force acting normally on a surface. In the diagram below, you can see a person is driving a nail in the wooden board. In this case, the force exerted by the nail on the wooden surface is called thrust because the nail is applying force normally on the surface. Another example you can take of a person standing on the ground. The person is exerting force on the ground due to his weight, and that force is acting normally on the ground. Normally, the force acting on the surface or thrust exerted by a body on a surface is always equal to the weight of the body. As thrust is a force, so its SI unit is Newton and CGS unit is Dyne. The gravitational unit of thrust in MKS system is kgf and in CGS system is gf. Thrust is a vector quantity. Now what is pressure? Pressure is the thrust acting per unit area of a surface. Mathematically, pressure is equal to thrust upon area. The SI unit of thrust is Newton and SI unit of area is meter square. So the SI unit of pressure is Newton per meter square or Pascal. Pressure is a scalar quantity. Now how we will define 1 Pascal? You know that 1 Pascal is equal to 1 Newton upon 1 meter square. So 1 Pascal can be defined as the pressure exerted on a surface of area 1 meter square by a force of 1 Newton that acts normally on it. Other units of pressure. Pressure is also measured in bar and millibar. 1 bar is equal to 10 raised to power 5 Pascal and 1 millibar is equal to 100 Pascal. Now the factors on which pressure depends. As it is clear from the formula, pressure is equal to thrust upon area. So it means that pressure depends on two factors. One is the thrust and second one is the area. Larger the thrust acting on a given area, greater is the pressure. Then second, pressure exerted by the thrust is inversely proportional to the area of surface on which it acts. Means larger the area on which thrust acts, lesser is the pressure exerted by it. For example, if we stand on loose sand, our feet will sink deep into the sand. But if we lie on the sand, our body does not sink into the sand. Though in both the cases, the thrust acting on the sand is the same because the thrust acting on the body on the sand is equal to the weight of the body. But in the second case, when we lie on the sand, the thrust acts on a larger area due to which the effect of thrust decreases, or you can say the pressure decreases. Ways to reduce pressure. For a given thrust, if we increase the area of contact, the pressure will decrease. Example, wooden sleepers are placed below the railway track because wooden sleepers will increase the area of contact due to which the pressure exerted by the rails on the ground becomes less. Second example is the foundation of high-rise buildings is always made wider because wider foundation increases the area of contact due to which less pressure is exerted by the building on the ground. Now ways to increase pressure. For a given thrust, if we decrease the area of contact, the pressure will increase. For example, it is easier to cut with a sharp knife because sharp knife has very thin edge. So large pressure can be created on the object when thrust acts on a small area. So the object can be cut with less effort. Another example, the tip of an awl pin is made sharp because sharpness of the tip decreases the area of contact with the object, due to which large pressure is exerted by the pin on the surface of the object and it can be driven into the object with less effort. Now pressure in fluids. Firstly, I will tell you what is a fluid. Any substance that can flow is called a fluid. So all liquids and gases are fluids. Now you know solids exert pressure on the surface of the object due to their weight. Same way, liquids and gases also exert pressure on the surface of an object or a container due to their weight. At the same time, they exert pressure on the walls of the container due to their tendency to flow. You can see from the figure, the arrows are pointing downward, means liquid exert pressure at the base of the container due to its weight and at the walls of the container due to its tendency to flow. Now a simple activity to demonstrate that liquid exerts pressure on the walls of the container. You have to take a container filled with water. Now make small holes at some distance from each other. You will find that the liquid will spurt out from each hole, which proves that liquid exerts pressure on the walls of the container at each point. Now as we are going towards the base, you can see that the water covers greater distance in the horizontal direction, which means that as we are going down, pressure is increasing, means liquid pressure increases with depth. So from this activity we conclude that liquid exert pressure on the walls of the container at each point, and second one, liquid pressure increases with depth. Now what are the factors which affect liquid pressure? Now pressure at a point in a liquid depends upon the following three factors. Depth of that point below the free surface, that is denoted by H. Then density of the liquid, denoted by the symbol rho. And third one is acceleration due to gravity. So mathematically, pressure in liquids is given by the formula P is equal to H rho G. Now G at a particular place remains the same. It means that pressure changes due to the change in depth of the point below the free surface and density of the liquid. Now what are the laws of liquid pressure? There are 5 laws of liquid pressure. First one is liquid pressure increases with depth. Second one is in a stationary liquid, pressure is same at all the points on a horizontal plane. Third point is pressure is same in all the directions about a point in a liquid. Fourth one is pressure at same depth is different in different liquid. It increases with the increase in density of a liquid. And fifth point is liquid seeks its own level. So these are the 5 laws of liquid pressure. Some consequences of liquid pressure: the walls of the dam are made broader at the bottom because liquid pressure increases with depth. So to withstand the high lateral pressure exerted by the liquid, the bottom of the dam the bottom of the dam is made thicker. It is clear from this diagram. Next is water supply tank is placed high. The reason is that as greater is the height of the tank, more will be the pressure of water in the taps of the house. Thus, for a good supply of water, the height of the supply tank must always be kept high. As it is clear from this diagram. Now gas bubble grows in size as it rises up. The reason is that when the gas bubble is at the bottom of the lake, total pressure experienced by the gas bubble is more because liquid pressure is more at a greater depth. But as the bubble rises, pressure exerted by the liquid on the bubble decreases, due to which the volume of the bubble increases. That is, the bubble grows in size.
Truck with thin tires looks odd, doesn't it? It doesn't look like it can manage the load it's carrying. As we've all seen, trucks need wide tires. On the other hand, let's look at a housewife trying to chop vegetables with a thick, blunt knife. She's not having much success. To chop efficiently, she needs a knife with a sharp blade. What is the significance of the width of the tires and the sharpness of the knife in these cases? This can be explained through the concept of thrust and pressure. The truck needs wide tires to reduce the pressure of the cargo. The knife needs a sharp blade to increase the pressure exerted on the vegetables. In this lesson, you will learn about thrust and pressure, with special emphasis on thrust and pressure in liquids. At the end of this lesson, you will be able to. Thrust is a vector force acting normally on a surface and is denoted by F. For example, consider the simple act of driving a nail into a wall with a hammer. The force that you exert on the hammer during this activity is thrust. Thrust is measured in dyne in the CGS system, and Newton denoted by N in the SI system. We have seen that nails have pointed tips to help us drive them into surfaces. Why is it important for a nail to have a pointed tip? For that matter, why is it important to have a sharp knife to chop vegetables? The force you apply in driving a nail or chopping vegetables is translated into pressure, depending upon the surface area of the object on which the force is applied. In other words, pressure is the amount of thrust acting on a unit area. Pressure is denoted by the letter P. Hence, pressure is calculated by dividing thrust with area. The lesser the surface area of an object, the more the pressure applied by that object. The pointed tip of the nail minimizes the surface area of the nail on which thrust is applied. Therefore, while driving the nail into the wall, the pressure of the hammer is maximized, which helps drive the nail into the wall. Pressure is scalar and is measured in dyne per centimeter square in the CGS system, or Newton per meter square or Pascal denoted by PA in the SI system. Another example will help illustrate further the distinction between thrust and pressure exerted by a body. Take a piece of foam and two identical metal blocks, say A and B, weighing 300 grams. The length, breadth and thickness of these blocks are 30, 20 and 10 centimeters respectively. Place the metal block A vertically on the foam and the other iron block B horizontally. Now let's compare the compression of the foam where blocks A and B are placed. The foam shows more compression where the metal block A is positioned vertically. Considering that both the blocks have the same length, breadth, height and weight, why do you think we see this difference in the compression of foam? This difference can be attributed to the difference in pressure exerted by each block. Block A was placed vertically over the sheet of foam, while block B was placed horizontally. The surface area of block A in touch with the foam is 200 square centimeters. On the other hand, the surface area of block B in touch with the foam is 600 square centimeters. Using the formula for pressure, we can now calculate the pressure of blocks A and B on the foam. The pressure of block A on the foam is 1,500 dyne per centimeter square. The pressure of block B on the foam is 500 dyne per centimeter square. Thus, in block A, the same thrust was acting on a smaller surface area. Hence, the pressure exerted by block A was higher. This explains why the foam showed more compression where block A was placed. The thrust exerted by a body remains constant, placed in any position. However, the pressure exerted by the body changes with a change in positions. Let's look at another everyday example. You may have used chairs in which the seat is created from plastic wave. These chairs are quite safe to sit on. However, if you try standing on such a chair, the plastic wire may give way under the strain. This is because when you stand on the chair, the area of contact becomes much smaller, and the pressure on the wire crosses the safety limit. In both the cases, the weight of the man, that is the downward force acting on the chair, is the same. However, the area on which it is acting has changed, leading to change in pressure exerted on the seat of the chair. So far, we looked at the examples of thrust and pressure in solids. However, thrust and pressure are equally applicable to the other states of matter, liquids and gases. Liquids and gases are collectively referred to as fluids, since block B was placed horizontally. The surface area of block A in touch with the foam is 200 square centimeters. On the other hand, the surface area of block B in touch with the foam is 600 square centimeters. Using the formula for pressure, we can now calculate the pressure of blocks A and B on the foam. The pressure of block A on the foam is 1,500 dyne per centimeter square. The pressure of block B on the foam is 509 per centimeter square. Thus, in block A, the same thrust was acting on a smaller surface area. Hence, the pressure exerted by block A was higher. This explains why the foam showed more compression where block A was placed. The thrust exerted by a body remains constant, placed in any position. However, the pressure exerted by the body changes with a change in positions. Let's look at another everyday example. You may have used chairs in which the seat is created from plastic wave. These chairs are quite safe to sit on. However, if you try standing on such a chair, the plastic wire may give way under the strain. This is because when you stand on the chair, the area of contact becomes much smaller, and the pressure on the wire crosses the safety limit. In both the cases, the weight of the man, that is the downward force acting on the chair, is the same. However, the area on which it is acting has changed, leading to change in pressure exerted on the seat of the chair. So far, we looked at the examples of thrust and pressure in solids. However, thrust and pressure are equally applicable to the other states of matter, liquids and gases. Liquids and gases are collectively referred to as fluids. Since all fluids have the tendency to flow, like solids, fluids also have weight, and this weight exerts a force on the walls and base of a container. We can demonstrate the effect of pressure in liquids through a simple example using a plastic bottle. Fill the plastic bottle completely with water. Then make a small hole in the lower half of the wall of the bottle. You will see that the water gushes out through the hole with considerable force. This force is due to the pressure of the fluid at that point. So, how do we calculate pressure in fluids? To derive an expression for pressure in fluids, let's consider a beaker filled with a fluid, say water, of density D, to a height h. Drop a coin with the area of cross-section A into the beaker. The volume of the water column above the coin V is equal to area of cross-section of the coin multiplied by the height of the water column. This gives us equation 1. Volume V is equal to A multiplied by H. The mass of the water in column M is the product of the volume of the water and its density. Thus, M is equal to V multiplied by D. Substituting equation 1 in the expression for mass, you get equation 2. That is, M is equal to product of A, H and D. As you know, weight of a substance is a product of its mass and the acceleration due to gravity, g. Therefore, weight of the water column, W, is equal to the mass of the water column multiplied by g. Thus, W is equal to M multiplied by g. Substituting equation 2 here, you get equation 3. Weight of the water column acts normally on the object. Thus, the pressure P acting on the coin is the ratio of weight of the water column to the area of the coin. That is, P is equal to W divided by A. From equation 3, we know W is equal to product of A, H, D and G. This gives the expression of fluid pressure P. P is equal to HdG, where H is equal to height of the water column, D is equal to density of the water, and G is equal to acceleration due to gravity. Using this expression, you can calculate the pressure applied by a fluid in the walls as well as the base of a container. The pressure at a point in a fluid is equal in magnitude in all the directions. Now let's look at some applications of the concept of pressure in our everyday life.